Welcome back. We're going to take a look at example 8.8. They've given us some price sales data and they've asked us for some various demand functions. So what I did to create these charts is I highlighted this area and I said insert scatter plot, and I took that. Now, let's change this scatter plot so it looks like the other ones to insert scatter plot. Let's make it look like there. There, it doesn't draw the lines. Now, if we want to draw this trend line and have it give us a an equation, we can say add a trend line. And we can trend regression type. Now we've got, as you remember, our different functions. We have all different kinds of functions. We have exponential functions. We have linear functions. We have logarithmic functions. It actually tells you a little bit about what these look like. You have polynomials where you have, it goes up, it goes down. You have power functions, moving averages, all sorts of power. Let's try a linear function and let's check these. Display the equation, so tell us what it is, and display the r squared, which is our correlation coefficient, so we know if we have a good correlation or not a good correlation. So I slide these up here so I can look at them. So there's a linear function which says y is equal to negative 9.5 and some data times our x, and our x in this case is price. So tell us the price, will predict the quantity demanded, plus 20,512. Now it says our r squared is 0.8331. Now that's what math is doing, is they're taking each one of these distances away from the line and going through a calculation to see how far is that away from the line. And if it's exactly on the line, the r squared will have a value of 1. If it's way away from the line, it'll have a value of 0. So something around 0.8 to 0.9. The closer to 1, the better the correlation you've got. You can visually look at this and say, the good news is we have some overs. There doesn't seem to be any consistency between what's over and under. And the r squared, although not great, is not bad at 0.83. So this linear model is not a bad predictor of demand given price. Now, you can do other functions, which we've done down here, to see if we get a little better. So we could have done, instead, we could have done an exponential function, which I've done down here. Now you get, amazingly, you get a very similar r squared. Little more complicated equation, 20,577 times e raised to the negative 5e raised to the negative, is that 0.04x. Now, if it's me, I'm going to go with the simpler equation, particularly when there doesn't seem to be any particular reason for me to want this more complicated equation. But that's how you can take a whole bunch of data, you can graph it, and then you can add these trend lines to see which kind of correlation might fit your data the best. Let's take a look at, if there's questions, let me know. You've got this Excel file on Blackboard. Let's do equation 8.9. This is where they give us crude oil prices, and we do sort of a trend line based on dates. So the same sort of thing, I've highlighted the data, and I went over and I said insert, I'll show you, I said insert a line, and there you go. And then I said add a trend line for us. And then you get to pick whatever kind of trend line you want. And you can compare them oftentimes, because very rarely do you get a perfect fit. Notice here we have an exponential function, which this is not good if it's beginning to consistently predict high or low. That worries you, because this line, this sort of polynomial, seems to be a better fit, particularly over this range. Oftentimes you'll find functions are good for some ranges, not good for other ranges. And so that's 8.9. Let's take a look at exam. If you have questions, let me know. Let's take a look at 8.10 example. This is sort of a what-if example. This is where we took a look at unit price as assumption, unit cost, fixed costs, demand, and quantity produced. So our model took our unit costs and then our quantity sold, again, is the minimum between the quantity produced and the quantity demanded. And then, of course, our revenues are simply our unit price times our quantity sold. Down here we have our unit costs, our quantity produced, and of course our variable costs are just going to be our unit costs times our quantity produced, fixed costs it gave us. So down here we had net income is just our revenue minus our variable costs minus our fixed costs. Now, I put in another thing in here because if you noticed, our demand in this case was more than the quantity we produced. So in this function, we actually had some lost revenue potential, which again I put in italics because the book didn't show it to you. But to me, that's somewhat important because notice that one could say we kind of played it safe. We had a lot more demand than what we produced. And if we had produced an extra 10,000 units, we would have had an extra $400,000 of revenue. And then down here I just gave you different scenarios. So here's the demand, and then nice thing about Excel is if you do the pattern and just fill it down, it understands the pattern you've given it. So I did revenue in different scenarios, cost, earnings, and then I added a column for lost revenue because notice you can begin to determine what kind of risks you want to take. For example, obviously in a perfect world, if we were that good, we realize that our demand is 500. So if we produced 50,000, if we'd produced more, look what would have happened to our earnings. We would have gone way, way up, right? As much as 400,000, right? In fact, if we had done, so notice the difference between 35 and 40,000. The difference in demand is only 14%. But look at the difference of not having look at the earnings difference, $200,000. So you want to do these sensitivity models to really understand how much revenue and how much inventory do you want to buy. So that's 8 examples, 8.10 through 8.12. All three of them are relatively the same. If you have questions, let me know.